Friends, welcome to the tutorial series on network analysis made simple. Electrical networks can be solved by using different methods such as branch current method, mesh current method, node voltage method, or even using the network theorems. In this tutorial, we will see network solution using branch current method. Friends, first let us see what is network solving. A network solving is a process of finding the unknown parameter in the network. The unknown parameter could be current through the network element or through a branch, voltage across any network element or across the branch of a network, power absorbed in a circuit element or circuit elements, and power delivered or power absorbed by the sources and so on. Then, what is a branch current method? A branch current method of solving a network can be defined as that in which branch currents are assumed as independent variables. Then, what are the network variables? Network variables could be assumed variables or derived variables, and they could be current variables or voltage variables, independent variables or dependent variables. We shall see all these different types of variables by taking a simple example. Now, let's take a simple example to find current flowing through all the resistances in the network shown in figure 1 using branch current method, for which we have to identify the junction nodes, branches, independent loops in the network before we start solving the network. I suggest you pause the video for a moment, write down your answers and then compare with the correct answers. According to me, there are three junction nodes in the network and they are A, B and C. And there are 5 branches in the network: branch 1, branch 2, branch 3, branch 4 and branch 5. And friends, there are 3 independent loops in the network and they are loop 1, loop 2 and loop 3 as shown in figure. If you are not sure about this, I suggest you go through my earlier video on network terminology. Friends, because we are required to solve the network using branch current method, let's assume the current flowing through the branch 1 as I1 and branch 2 as I2 and branch 3 as I3 as shown in figure. By applying Kirchhoff's current law to junction node A, we get current flowing through the branch 4 as I3 minus I1 and current flowing through the branch 5 as I2 minus I3. Now, if you apply Kirchhoff's current law to junction node C, you see that I1 and I3 minus I1 and I2 minus I3 are coming towards the junction C and I2 is going away from the junction C. And if you find out I1 plus I3 minus I1 plus I2 minus I3, that becomes equal to I2. It means the Kirchhoff's current law will hold good in all the junction nodes in the network. Now, you see that there are 3 unknowns I1, I2 and I3 and we need 3 equations. So, by tracing loop 1 in the clockwise direction and writing the Kirchhoff's voltage equation, we get minus 12 plus 4I1 minus 6 into bracket I3 minus I1 is equal to 0. And if you rearrange this equation, we get 10I1 minus 6I3 is equal to 12. Let it be equation 1. Similarly, by tracing the loop 2 in the clockwise direction and writing the Kirchhoff's voltage equation, we get plus 6 into bracket I3 minus I1 minus 36 minus 12 into bracket I2 minus I3 equal to 0. And by rearranging it, we get minus 6i1 minus 12i2 plus 18i3 is equal to 36. Let it be equation number 2. Similarly, tracing loop 3 in the clockwise direction and writing the Kirchhoff's voltage equation, we get plus 12 into bracket I2 minus I3 plus 3I2 minus 24 is equal to 0. By rearranging it, we get 15I2 minus 12I3 is equal to 24. Let it be equation number 3. And if you are not sure about how to write the Kirchhoff's voltage equation for a loop, I suggest you go through my earlier video on Kirchhoff's laws. Friends, the balance equations, equation number 1, 2, 3 are reproduced here for convenience. By solving these three simultaneous equations, we get I1 is equal to 9 amperes, I2 is equal to 12 amperes, and I3 is equal to 13 amperes. But we want current through all the resistances in the network. Hence, current through 4 ohm is I1, which is equal to 9 amperes. Current through 3 ohm, I2 equal to 12 amperes. Current through 6 ohm, which is I3 minus I1 equal to 4 ohm. And current through 12 ohm, which is I2 minus I3, and that is equal to minus 1 ampere. Friends, now let me explain what are network variables. If you recall, while solving the network, we assumed branch currents I1, I2 and I3. Then, applying Kirchhoff's current law to junctions, we found currents in other branches of the network, and hence these assumed current variables are called as independent variables. Later what we did, while writing the Kirchhoff's voltage equations for the loops, we found voltage across each passive elements. These voltage variables are derived variables using independent current variables assumed. Hence, these derived variables using independent variables are called as dependent variables. Now you have understood what are independent variables, what are dependent variables, what are current variables, and what are voltage variables. Friends, now let me tell you the points to remember and recall before you solve any network. The first is understand the connectivity of the given network by identifying the junction nodes, branches, and independent loops correctly. If any branch or branches contain series and parallel connected elements, find their equivalents and redraw the circuit. If the number of loops could be reduced by source transformation, do it. After all these steps, assume the required number of independent variables, which are branch currents in our case now. Apply Kirchhoff's current law for each junction node and find the other branch currents in terms of assumed independent variables. Identify the independent loops and write the Kirchhoff's voltage equations. Reduce the equations in the order of independent variables. For example, AI1 plus BI2 plus CI3 is equal to D, where A, B, C and D are constants obtained after reduction. Friends, remember, the number of equations required to solve the network will be equal to the number of unknowns. Friends, let's take another example to find all the branch currents in the network shown in figure 1 using branch current method. Before we start solving, let me ask you a few questions to understand the connectivity and the types of sources in the network. I suggest you pause the video for a moment, Write down your answers for the questions and then compare with the correct answers. If you are ready, my first question is identify the junction nodes in the network. There are four junction nodes and they are A, B, C, and D. Next, identify the branches in the network. Friends, there are seven branches in the network and they are B1, B2, B3, B4, B5, B6, and B7 as shown in figure. My next question is identify the different types of sources present in the network. Friends, there are four sources. One is ideal current source of 19 amperes. Next is ideal voltage source of 240 volts. And the third is dependent current controlled voltage source of 4i4 volts. And the fourth is dependent current controlled current source of 2i2 amperes. If you are not sure to identify these sources, I suggest you go through my earlier video on voltage and current sources and their handling. Now, we are required to solve for unknowns using branch current method. First, let us assume the current flowing through branch 1 as I1 and current flowing through the branch 2 as I2 as shown in figure. By applying Kirchhoff's current law to junction node A, we get current in branch 5 as 19 plus I2 minus I1 amperes. And by applying Kirchhoff's current law to junction node B, we get current in B6 equal to I2 amperes. Similarly, by applying Kirchhoff's current law to junction node C, we get current in B4 is equal to 19 plus I2 minus I1 amperes. And you know that there are only two unknowns I1 and I2 and hence we need two equations. Therefore, by writing the Kirchhoff's voltage equation, tracing the loop CABC, we get minus 4i4 plus 5i2 minus 10i2 is equal to 0, but i4 is equal to 19 plus 2i2 minus i1, and by substituting this value of i4 and rearranging the equation, we get 4i1 minus 13i2 is equal to 76 and let it be equation 1. Similarly, by writing the Kirchhoff's voltage equation, tracing the loop DCBAD, we get minus 240 plus 10i2 minus 5i2 minus 40i1 equal to 0. And by rearranging, we get minus 40i1 plus 5i2 is equal to 240. Let it be equation 2. By solving these two simultaneous equations 1 and 2, we get I1 is equal to minus 7 amperes and I2 is equal to minus 8 amperes. Friends, we are required to find all the branch currents and we know that I1 is equal to minus 7 amperes and hence the true current will flow towards A. Similarly, I2 is equal to minus 8 amperes and hence the true current will flow towards B as shown in figure. And also we know that current in branch B3 is 19 amperes flowing towards A. And we know the equations for all the branch currents and hence current in B4 is equal to 10 amperes, current in B5 is equal to 18 amperes, current in B6 is equal to 8 amperes and current in B7 is equal to 16 amperes. Friends, let's take another example to find all the branch currents in the network shown in figure using branch current method and to show that the total power delivered is equal to total power absorbed. If you observe the network, you find that there are four junction nodes A, B, C, and D, and there are six branches B1, B2, B3, B4, B5, and B6. Now, Let's assume independent variables. Let I1 be the branch current in branch 1 and I2 be the branch current in branch 2. Applying Kirchhoff's current law to junction node B, we get the current in B3 is equal to I1 plus I2. Similarly, by applying Kirchhoff's current law to junction node A, we get a current in branch B4 is equal to I1 minus I2. And by applying Kirchhoff's current law to junction node C, we get B5 is equal to I2 plus 2 amperes, and we know that the current in B6 equal to 2 amperes. Now, we know all the branch currents in terms of independent variables I1 and I2. Therefore, we need two equations to solve this network. Now, by tracing the loop dBAD and writing the voltage equation, we get 10 minus 2I1 minus 8I1 minus 2 is equal to 0, from which we get 10I1 is equal to 26 and I1 is equal to 2.6 amperes. Similarly, by tracing the loop dBCD and writing the equation, we get 10 minus 4I2 minus 6 into bracket I2 plus 2 is equal to 0. By rearranging, we get minus 10I2 is equal to 2, and hence I2 we get equal to minus 0.2 amperes. Therefore, current in branch B1 is equal to I1, which is equal to 2.6 amperes flowing from B to A. Current in branch B2 is equal to I2, which is equal to minus 0.2 amperes, which is flowing from C to B. Current in branch B3 is equal to I1 plus I2, which is equal to 2.4 amperes flowing from D to B. And current in branch B4 is equal to I1 minus 2, which is equal to 0.6 amperes flowing from A to D. And current in branch B5 is equal to I2 plus 2, which is equal to 1.8 amperes flowing from C to D. Friends, true directions and the value of currents in each branch are indicated in figure 4. Do you know that the sources either can deliver power or absorb power? To find the power delivered by the source, we know that if the current in the branch containing voltage source leaves the positive terminal of the source, the power is delivered by it. Similarly, if the current enters the positive terminal of the voltage across the current source, the power is delivered by it. Hence, to find the voltage across the current source, if we write the Kirchhoff's voltage equation from A to C, we get VAC is equal to 2 into 2.6 plus 4 into 0.2, which gives us 6 volts with plus terminals towards C and minus terminals towards A. So, in the network shown in figure, both sources deliver power. Friends, first let us find the total power delivered by the sources. Now, power delivered by the voltage source is equal to 10 into 2.4, which comes to 24 watts. Power delivered by the current source is equal to 6 into 2, which comes to 12 watts. And hence, total power delivered is equal to 36 watts. Now, you know that the power absorbed in the resistance is I squared R watts, and hence the total power absorbed in all the resistances is equal to 2.6 square into 2 plus 0.2 square into 4 plus 1.8 square into 6 plus 0.6 square into 8, which comes to 36 watts, and hence it is proved that the total power delivered is equal to total power absorbed in the network. Friends, I hope I have made it clear the different aspects of solving the network using branch current method. And I suggest you get the mastery over identifying the junction nodes, loops, and branches in the network, and the network solving will be very easy. Thank you for watching.